Okay, today we're going to look at section 3.5, rational functions. We skip section 3.3 and 3.4, and we do not continue past 3.5 in chapter 3. So, rational functions. What is a rational function? Well, we start with let P of x and Q of x be polynomials where Q of x does not equal 0. A function f defined by f of x equals P of x over Q of x is called a rational function. Keep in mind the domain of a rational function is all real numbers excluding the real zeros of Q, or anything, all real numbers in the domains of Q of x, in the domain of Q of x. Excluding the real zeros of Q. So let's look at this here. First function is 1 over x. Well, we can't factor any, it's simply 1 over x. And we note that the domain cannot contain 0. Next function here, we look at 5x squared over 2x squared plus 5x minus 12. Well, looking at it, it's factored. We can factor it this way. We can solve each of these factors for equal to 0. And we note that x cannot equal 3/2 and x cannot equal -4. Then here, again, x plus 3 over x squared plus 4. X squared plus 4 cannot be factored, and there is no value of x that'll make the numerator or denominator 0, so it's all reals. So here's what we look at. Look at something like this. Let's go with something like 1 over x minus 2. Let's see what happens here. So what happens? F of x equals 1 over x minus 2. What happens to this? Well, as x approaches 2, we start with, well, let's just do f of 3. And that's 1 over 1. F of 4, well, that's 1 over 2. Hold on. F of 4, yep, 1 over 2, and so forth. And what we see is it's getting closer to 0, but it'll never reach 0 because this will never be 0. Now let's see what happens as y approaches 2, or as x approaches 2 from this side. What's happening? Okay, so we had 2. We had 3. So what about 2.5? Now if x is 2.5, we get 1 over 0.5, which is 2. And if x is 2.25, we get 1 over 2.25, which is 4. So what we have going on here is something like this. And then if we go this from the negative, what we're going to see is the same thing. And it's almost like there's a fence here at x equals 2 and a fence here at y equals 0. That's what we're looking at. Which brings us to, we'll start with vertical asymptote. The line x equals c is a vertical asymptote of the graph of a function if f and f of x approaches infinity or negative infinity as x approaches c from either side. Infinity, negative infinity. Identifying a vertical asymptote of a rational function. So if we consider a rational function f defined by f of x equals p of x over q of x, where p of x and q of x have no common factors other than 1. If c is a real zero of q of x, then x equals c is a vertical asymptote. So let's start out simple. About f of x equals 3 over x plus 1. So what we do is we find the zeros for the denominator, -1. Now in this case, I have an asymptote at x equals -1. Looking at another one, we'll call this h of x equals x plus 7 over 2x squared minus x minus 10. And this will factor 2x minus 5 times x minus 4. So in this case, I have 2x minus 5 equals 0, 2x equals 5, x equals 5 halves, and I have x minus 4 equals 0, x equals 4. So I have 2 vertical asymptotes. And then looking at something like this, g of x equals 5x over x to the 4th plus 1. There are no zeros here, so there are no vertical asymptotes. So, avoiding mistakes, page 348, this says, procedure to find a vertical asymptote of a rational function is given under condition that the numerator and denominator share no common factors. This important observation can be illustrated by this graph on page 248, figure 319. Because when we factor out, what we have is f of x equals 2x squared plus 5x plus 3 over x plus 1. And this can be factored to x plus 1 times 2x plus 3. And the thing we would do would be cancel this out. So we would just get a line, which is shown in the graph on the page. And the thing is, though, we still have to take into account this. So we would have this line like so, but at -1, we would put an open circle. So you have to be careful of that. That doesn't come up very often, but it can. Okay, looking at a horizontal asymptote. The line y equal d is a horizontal asymptote of the graph of a function f if f of x approaches d as x approaches infinity or negative infinity. So it was like our 0 here, y equals 0. How to identify a horizontal asymptote of a rational expression? So if we have f as a rational expression defined, and again, we just used a sub n, x sub n, and on over b sub m, x sub n, b sub m, or x sub m, on and on to the so let's go back here. this was this one here. They're equal, right? Because when squared, squared, and that's y equals 0. Lastly, or n is less than m. That wasn't that one, that was this one. Sorry. This is the graph of 1 over x. Actually, 1 over x minus 2. So here, the degree is 0, here it's 1. So m is less than n, so we have y equals 0. Then if n equals m, the line a sub n over b sub m is the horizontal asymptote of f. So let's look at some of these. Look at f of x equals 7x squared plus 2x over 4x squared minus 3. So my degree of the numerator is 2, the degree of the denominator is 2. So they're equal. So this is y equals 7/4. That would be my horizontal asymptote. Okay, how about m of x equals 4x cubed plus 2 over 2x minus sub x equals 5 over 4x squared plus 9. In this case, the degree of the numerator is 0, the degree of the denominator is 2. So m is greater than m, so y equals 0 would be our asymptote here. Okay, so vertical asymptotes cannot be crossed under any circumstances. Unfortunately, horizontal ones can be. So, given g of x equals 3x squared plus 4x minus 3 over x squared plus 3, we want to determine the horizontal asymptote and the point where the graph crosses the asymptote. So what is our asymptote? Our degree of the numerator is equal to the degree of the denominator. So a over b. Y equals 3 over 1. So y equals 3. So this is what I'm looking at here. At 3, I have a vertical asymptote. Now, can I plug 3 in this equation and get a valid result? So what is g of 3? Actually, no, that's not what I want. I want to know, when does this equation equal 3? 3 equals 3x squared plus 4x minus 3 over x squared plus 3. Go ahead and multiply the x squared plus 3 by both sides, and we get 3x squared plus 9 equals 3x squared plus 4x minus 3. Subtract 3x squared from both sides, and they cancel out. Add 3 over here, and we get 12 equals 4x. Divide by 4, and we get 3. So it crosses at 3, 3. Here's actually what this looks like. It goes up, it crosses, and then it starts coming back down and doesn't cross. And there's another side over here, like that, for the full graph. Okay, so that's horizontal and vertical asymptotes. The next one we look at is something called a slant asymptote of a rational function. Rational function will have a slant asymptote if the degree of the numerator is exactly 1 greater than the degree of the denominator. To find an equation of a slant asymptote, divide the numerator of a function by the denominator. The quotient will be linear and the slant asymptote will be in the form y equals the quotient. So let's see. Determine the asymptotes. G of x equals 2x squared minus 9 over x plus 1. Well, first we have a vertical one. That's the easy one. Right here, x equals -1. Set it equal to 0, solve for x. Now, my degree of the numerator is 2, degree of the denominator is 1. So that means that we meet this slant asymptote. So here's how us old folks do this. Now, one thing you have to do is put in the missing values. 0 times x. Now, there are other ways to do this. I'm not familiar with them offhand. So what we do is we take x, and how many times will x go into 2x squared? Well, 2x. So 2x times x is 2x squared. 2x times 1 is plus 2x. Then I subtract all of that, and this is 0, and this is minus 2x, and bring down this minus 9. Now, how many times will x go into negative 2x? Well, minus 2. Gives me minus 2x minus 2. Again, subtracting this, I get 0 minus 7. And this is the equation for my slant asymptote. Y equals 2x minus 2. Okay. Okay, I don't need to do that. So, how do we do this? So, graphing a rational expression, a rational function. Consider a rational function f, defined by f of x equals p of x over q of x, where p of x and q of x are polynomials with no common factors. So here's the process we need to do. Determine the y-intercepts by evaluating f of 0. Determine the x-intercepts by finding the real solution of f of x equals 0, which is when the numerator is equal to 0. So when p of x equals 0, identify any vertical asymptotes, graph them as dashed lines, determine whether the function has horizontal or slant asymptotes, or neither, and graph the asymptotes as a dashed line. Determine whether the graph crosses a horizontal or slant asymptote if applicable. We can do a test for symmetry. If it's easy to apply, use symmetry to plot additional points. Plot at least one point on intervals divided by x-intercepts, vertical asymptotes, and points, and sketch the graph. So let's look. And let's do f of x equals x minus 1 over x plus 4. So f of 0 is 0 minus 1 over 0 plus 4, which is 1/4. So I have the point 0, 1/4. And 0 equals x minus 1 over x plus 4. When x minus 1 equals 0. When x equals 1. So I have 1, 0 as a point. My denominator is x plus 4. So x equals -4 is vertical asymptote. X equals -4. My numerator and denominator have the same degree. So my horizontal asymptote is y equals 0. And if you have a horizontal asymptote, you will not have a slant asymptote. You'll have one or the other, but not both. So let's see what we have so far here. I have x equals -4. 1, 2, 3, 4. That's one asymptote. Dotted line, x equals -4. Y equals 0. Actually, let's do this. Make an adjustment here since I'm over on the negative side. 1, 2, 3, 4, -4. X equals -4. Okay, I have an asymptote y equals 0. That's that. I have the point 1, 0. So you see I'm crossing that asymptote already. Huh. That's not right. I did that backwards, didn't I? Horizontal asymptote. Let's go back and look at this. When they're equal, it's a over b. So it's actually should be y equals 1. You got to be careful with this stuff. It's easy to get lost. Which makes more sense. Let's see. Y equals 1. Y equals 1. X equals -4. Then I have 1, 0. And I have 0, 1, 4. Zero, -1/4. Down here. So this is what this part's going to look like. And then this part's going to look like this. Okay. So that is that. That is it for section 3.5. Time.